Okay, 7.3 is polynomials. So with this whole chapter also being called polynomials, we were led into 7.3 with 7.1, which was all about multiplying, dividing monomials in 7.1 and then 7.2. So instead of just being one term, now these are going to be multiple terms. So first we'll have to identify a polynomial, and we're told in the instructions to state whether each expression is a polynomial. That question will be answered with yes or no. If it is one, we'll identify it as a monomial, binomial, or trinomial. So off to the side, let's have you write down mono, bi, tri. Well, how many wheels are on a tricycle? 3. How many wheels are on a bicycle? 2. And no, we're not going to call it a unimonomial or a uninomial or anything like that, but if somebody spoke in one tone, you would call them monotonous, and that's only having like one tone. So only when you hear mono at the beginning of the word, that means one usually. Write the following down, pause the video, I'm going to talk through each of these next. Okay, so if this were our bookwork, I could separate it with a semicolon, and I would say, well, yes, this is a monomial. There's no division. I'm sorry. Yes, it is a polynomial. There's no division or anything going on. But when I look at it, I'm separated by a minus sign, so there's one and then a second term, and also I can't combine either of those because they have separate variables, so these are not like terms. So yes, this is a binomial, and we don't have to explain why. The next one has two separate terms, but the issue is we have a negative exponent, which means that this would be 5 over n squared in that second of those two terms. And whenever you have division of variables involved that you can't simplify, this would be no, it's not a polynomial. Now we're stating whether or not it's a polynomial. We do not have to take this further and say which type it is, because we wouldn't be able to follow that second direction. -8. Yes, even though it's just a constant unattached to a variable or anything like that, it is still a polynomial. And then more specific than calling it a polynomial, this only has one term, so I'm going to call this a monomial. Now this last one is going to require a couple steps. I'm going to scan through this and see if anything can be combined. Nothing has x squared with it, so I'll just rewrite 4x squared, but I do have 5x and x. And a while ago, when you combine like terms, you learned that if it has the same letter to the same power, you can combine those. And then this polynomial is not just a polynomial, it is a trinomial. Hopefully those made sense. There's a couple in the book that you can test out, but you'll have answers to problems in the back of the book to check on the odd ones as you do these on your own. I think that this identification problem is mostly straightforward. Okay, let's develop our own polynomial. I think these are actually fun problems. I want you to get a ruler out, and on 3 lines, draw a vertical line, and we're going to end up drawing a rectangle. So as you draw this rectangle, make it wider than it is tall. But then included in the center of that rectangle, I want you to draw a circle. Your circle hopefully looks a little bit better than mine, and it will actually be tangential here and there, and that means it's just barely touching. The center of the circle usually has a dot, and we can drop a line from the center of the circle anywhere to any point on that and label that with R for the radius of that circle. But the width of this whole rectangle is going to be represented just by the letter B. We are told to write a polynomial to represent the area of the shaded region. So with your pencil, go ahead and shade here and here, but not inside the circle. Now these are fun problems in my opinion, because you have to kind of reason through these. Well, I want to know the area of just the blue shaded regions. So when you're taught these, you can think of what would happen if I had that same rectangle with the width of B, and it was all completely shaded in. Well, what would that entire area be? Well, it's not like it's b times b because that's not a square. So over here, let's write rectangle. So this is the entire rectangle. And its area alone is going to be length times width. So it's going to be b, which is the length. Well, how tall is this rectangle? What is its width? Well, you would know that the radius, even though I drew it at an angle, is really here and here. So if I want to write it in terms of the variables they give me, it would be twice the radius. So I'll go ahead and I will label this as 2r, meaning that this is the height of that rectangle. So the rectangle's area is going to be b times 2r. So that's how I got the rectangle. But now I'm going to find the area of the circle. From memory, awesome. If you know this, that's great. If not, make a point to memorize it. I'm going to clear away my rectangle so I can now talk about the circle and the area I have. Well, the circle is going to have area of pi r squared. That's just a formula you need to memorize. And now I have to think about, well, how would I get just the shaded region? Well, the shaded region would be the entire rectangle minus that inside circle, and then I would be left with a region here and a region there once I've taken the circle away from that rectangle. Now once you see these, they're kind of easy to figure out, but even now it might not click, so keep practicing them and seek teacher help if you need it. So the rectangle is the bigger of the two shapes. I'm going to write this as rectangle minus circle area, and I'm going to label it clearly, and I'm going to write 2br minus pi r squared. And that is a polynomial because it is made up of not one, but two terms that will end up giving you the area of this blue shaded region. Let's check out a second one. Practice is going to help these out. Imagine a larger rectangle. With your ruler, draw a larger rectangle than one that's included in the center. The outside rectangle has a length of 4x and a height of 2x. Now when I'm labeling geometric drawings, I feel like this is clearly attached to that side, but if it wasn't, it might be unclear to who's looking at it. So there's an extra step in a lot of geometric equations, and a lot of geometric drawings, where you may have to look at it for a moment and see what's conventional to figure it out. Now this inside length is going to be 2x, and this inside width is going to be x. Well, the shaded region that we're interested in finding is kind of similar to the last one. It's this outside region. So in my head, I'm picturing this as being a large rectangle totally filled in. So if I took the total area of the bigger one and then I took away the area of the thinner one, I would be left only with that kind of window frame looking shape. You can take scratch paper out and re-sketch that and see if you agree with me, and then also re-watch the video too to see the explanation, because I think it might be helpful. Now these are both rectangles, so it's your call. You can either write large or large rectangle. I'll write large R-E-C-T and I'll underline it. This first one's a little bit more straightforward, and the reason it's more straightforward is because the length is labeled. I'm skipping a line just so it doesn't overlap with what I have. The width is clearly labeled. I don't have to do any work to find it, and I think I will left to right go ahead and simplify this as 8x squared. But then when I look at the inside rectangle, it's smaller, so I'll label this as the smaller rectangle. And actually I misspoke, this one's actually not as crazy as I thought it was. The smaller rectangle has a length of 2x times x for the width, and I'll get 2x squared. so that when I figure out the entire deal, large minus small, to give me the shaded region shown here, I'm going to write 8x squared minus 2x squared, which simplifies to 6x squared. And the cool thing is, no matter what numbers we end up plugging into this drawing, we'd be able to find the answer using this 6x squared expression. So we were representing an abstract idea through numbers. And so what this really is if I look at this, this is half of that. And there's definitely patterns you can look for there. The other thing, too, is, this is an area problem, and if the book designed it correctly, this should be a positive number, because we're talking about area. Well, x, no matter what it is, when squared, will become positive. Times 6 would stay positive. So there's sometimes ways you might be able to look at it from different angles to see if you agree with the work you did or not. We'll stop this video before moving into other types of problems.